Hello, you have to finish working on this question. Let's do it together. So, by the way, remember, like before doing this work, remember in the previous similar example, the variance was 144. 144. If you use that, what would be the variance of this variation? First, you have to calculate the mean. The mean is different. Now, previously the mean was $6, but because of $1 fee, the mean is $5 now. Or you may recalculate the probability weighted outcomes and sum them again, and then anyhow you are going to get $5, right? So this is the same variable, like so transformed random variable by taking -1. So the mean also preserves the same linear transformation. And it's easy to see that the mean is $5. You expect to make $5 profit from this lottery. Now let's calculate the deviations. Minus 16 minus mean is minus 16. Excuse me. Minus 11 minus 5, the mean, equals minus 16. And minus $1 if you lose $1. This is $6 below the expectation. And if you gain $19, it's $14 above the expectation. So the deviations are easily obtained by subtracting the mean $5 from those three outcomes. In this process, I do not use the probability at all. Probability does not enter at all. And the square deviations are simply squaring those guys, deviations, right? So you get square deviations. And also I have not used the probability, but the probabilities are now the probabilities for these squared deviations as a transformed random variable. Then finally, you have to calculate the mean of the squared deviations. So three possible outcomes for the squared deviations and their probabilities. Multiply, 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 sum. That's the variance, which is 144, which is the same variance as in the original example. So what we learned is even if we subtract 1 from all the outcomes, it does not affect the variance, right? So like let me compare. Here there are deviations and square deviations. Remember those numbers, deviations. Deviations, minus 16, minus 6, plus 14. And go back, uh, no difference, right? This is the so remember this is the original example, minus 10, 0, 20. So original example, and deviations are the same. So then automatically square deviations would be the same, right? Deviations are same. The reason why the deviations are the same in the original example and in the variation is because the only difference is we paid $1. We deducted $1 from every income. Every outcome. So every outcome, for each outcome, we deducted $1. So this deduction, so everything moved backward like this, like shift by -1. And then because of that, the mean also shifted -1, right? So when an observation moves to -1, the mean also moves to -1. That means their distance does not change. That's reflected on this deviation. So if everything shifts parallel to one direction, to a direction, then the distance does not change. Everything is parallel shift. So the variability is not affected at all. it's only about where the center is, right? So taking like subtracting one only affects the location, but not about the distance. So that's why that's the intuition behind this result. The variance is the same. Now, so we are going to study another example. So now we are going to increase. So from the original, excuse me, from the original example, now we are going to multiply 10. So it's like you increase your investment. You bought 10 stocks instead of one. So if you lose $100 now. But if you gain, then you get $200 now. Probabilities are the same, right? So everything is scaled by 10. Then what would be the variance for this larger scale investment? Try this question, and or you may guess before doing the algebra, guess what would be the answer. So remember, in the original example, the variance was 144. So the this variance in this example, the variance will be related to something like this, 144 and 10. So guess and then do the algebra. I will. So pause the video, do the work, and now I'm going to show you how to do it. Again, the first thing you have to do is to calculate the mean. So it's exactly what we did earlier. Now the mean is 60, because in the original example the mean was $6. But because you increase the scale by 10 times, now the mean increases by 10 times too. So multiplying 10 is another linear transformation. Multiplying something or adding something is a kind of linear transformation. So here, multiplication of 10 is preserved in the mean. So it's 10 times larger than the original mean. And now calculate, because you have the mean, you can calculate the deviations. When you lose $100, it is $160 below your expectation. If you gain nothing, lose nothing, then it's $60 below your expectation, and $200 is $140 above your expectation, right? So this is the deviation, the difference between outcome and the center, the mean. The mean is 60, and deviations are like this, and now then square them. The numbers get bigger because 10 was multiplied. But what you need to see here is, what I want you to see here is that it's not inflated simply by 10, but by 100, right? Let me compare the numbers to the previous ones. So here, think about, like, remember, minus 16 minus 6 plus 14, 256, 36, 196, right? Now, move to this example. Here, deviations have another zero, additional zero in deviation, but square deviations have two more zeros compared to the previous example. So there are two more zeros. They have another zero because everything is squared. So multiplication of 10 now becomes multiplication of 100. Multiplication of 10 squared, because 10 is also squared. So it's like multiplying 100, not just 10. This is the major difference. As a result, if you calculate the variance equals this, which is, so now the variance is the mean of the square deviations. So multiply an outcome of square deviations to its probability, this one, and then multiply outcome and probability, multiply, and these are probability weighted square deviations. Sum them, that's the variance. This is the mean of the square deviation. And as you know, as you see, the original variance was 144, but now it becomes 100 and 14,400. So it becomes 10 or like not 10 times larger, but 100 times larger. This is uh, this is tricky, and it is actually a problem. So let me compare three three examples. Say I will simply write it as x, y, z. So in the original example, the mean and the variance was 6 and 144. And when you subtract 1, if you subtract 1, then the mean was subtracted by 1, but the variance does not change, right? So it's interesting. And now if you compare the first and the third examples, it's a multiplication of 10. So expectation is multiplied by 10, right? 6 and 60. But its variance is multiplied by 100. As I explained earlier, multiplication of 10 is squared, so it becomes multiplication of 100. So now if you put them together like this, the expectation is pretty nice. It's really well behaved. Exactly moves as you change the outcomes. Like if you subtract 1, mean changes by -1. If you multiply 10, then mean is multiplied by 10. But variance is not regular. It's not like there is no like a clear rule. So when you subtract 1, no difference. But when you multiply 10, it inflated like it inflates 100 times. So you get even larger. So this is this 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 is what makes the variance complicated. And in the previous chapter, when I explained the means, the linear transformation formula is a nice property of the mean. You may think it's obvious, but actually, it's a really nice property. Not every measure has the same property like that, like the mean. So this is an example. Variance does not preserve linear transformation. So even in the linear transformation, variance have to be recalculated. Has to be recalculated. So now let me make it a simple formula. Suppose that x is the original random variable and y is a transformation of x defined this way. Multiply a number and add a number, right? And then we already learned that the mean preserves that relationship. Mean preserves exactly the same linear transformation between x and y, but variance is not. Variance does not preserve the relationship. First, addition plus b disappears. It has no effect on variance. And multiplication has a distorted effect. It is also squared together with the square deviations. So multiplication has some effect on the variance, but it is not what you expected. So this is a simple uh, result. So we are going, this is a problem multiplying a, so linear transformation distorts the variance. So we are going to construct another measure that adjusts for this scale problem. And I will do that in the next video. So that is the standard deviation. Okay, then see you there. See you in the next one. Bye.